Hello viewers, today in this part of the talk we will discuss some more extended examples of specific heat of solid, and along with that we will discuss the mechanism of thermoelectricity. So, the outline for the talk today is we will discuss the specific heat capacity of silicon and gallium arsenide, the thermal conductivity of solids, thermoelectricity such as Thomson effect, Seebeck effect, Peltier effect, and then finally, the Thomson relation which correlates the three different types of thermoelectric phenomenon. Specific heat of silicon. As we discussed in our previous section that the specific heat of solid can be calculated by following the different models of specific heat. But when it comes to calculation of the specific heat of silicon, then it is little bit difficult to use Debye's model, though it will give somewhat accurate result, but it will not be exactly the value that you get experimentally. The reason being, in Debye's theory, he considered the continuous medium to have all the frequencies of elastic waves. Whereas, if we think of silicon crystals, in that the frequency that is obtained at the minimum scale is of the order of the interatomic spacing. That means, the wavelength related to the frequency is of the order of interatomic spacing. So, in this case we have to have a different treatment for the calculation of the specific heat of solid. So, to find that out, we can consider a infinitely long one dimensional atomic lattice for silicon. As you can see from the diagram, we have considered few black dots which represents the atoms of the lattice or atoms of the silicon lattice. Now, because this is an infinitely long lattice, we can consider a smaller section which is there in the diagram, and we can implement the equations of motion because the atoms are vibrating, and these black dots, as they represent the atoms in the lattice, we can have a mass associated with these atoms, and let that mass be small m, and these atoms are equally spaced. Now, if we consider in this particular case the interaction of atom only with the neighboring atoms, and if we apply Hooke's law to this motion or the vibration of atoms, then we can write the following equation of motion for the nth atom in the diagram, which is m x n double dot is equal to minus f x n minus x n minus 1 minus f x n minus x n plus 1, and the solution for this particular equation can be x n as a function of time is equal to e exponential minus I omega t minus q n a. By using this solution in the equation of motion, we can get the frequency of the vibration or the modes of vibration, and which can be represented in the following way, that is omega is equal to omega max sin q a by 2, where omega max square is equal to 4 f by m, where f is the constant in Hooke's law and q is the wave vector. So, the relationship that we got for the frequency of the vibrational mode basically gives us the relationship between the frequency and the wave vector. But for a continuous string, we know that the relationship for frequency and the wave vector is nu is equal to q c by 2 pi, and this relationship is true for identical mass points if Q A is much less than 1, and the physical meaning is that the wavelength must be much smaller than the interatomic spacing in the lattice. So, the difference between the two is that in continuous string the velocity is independent of wavelength, whereas for a string of mass points the velocity depends on the wavelength. Now, if we represent the relationship between the frequency and wave vector in terms of graph, then we can get a nice graph for both the cases, that is for a continuous string as well as a string having mass points. And as you can see on the left extreme of the slide, we have shown the relationship graph between frequency and the wave vector, and this particular graph is called dispersion graph. And here the curve A represents the relationship between frequency and wave vector for a string having mass point, and curve B represents the dispersion curve for a continuous string. Now, it can be shown that the wave vector is periodic in nature, that is Q m is equal to Q plus 2 pi m by A, where m is integer values. So, it means that within the boundary of the Brillouin zone, that is from minus pi by A to plus pi by A, we can find out all the modes of vibration associated with the particular lattice. We do not need to go for the higher boundary zones to find out the vibrational modes. Now, since there is a maximum frequency which can propagate in the medium, this particular lattice or this particular crystal acts as a low pass filter, where the maximum frequency is represented as nu max is equal to 1 by pi root over of f by m. Now, after getting the value of the frequencies of mode of vibration, we can use the boundary conditions to find out the energy associated with the crystal. Now, we can easily find out the number of modes of vibration for this particular system by finding out the number of particles vibrating in the system. Now, once that is known, we can find out the average energy for each mode of vibration by using the following equation, that is average energy E is equal to h cross omega by exponential h cross omega by k t minus 1. So, with this information now we can find out the total energy of the finite one dimensional lattice. Now, the energy expression that we will get from these boundary conditions is the following, that is E is equal to L by pi integration 0 to pi by A h cross omega q divided by exponential h cross omega q by k t minus 1 dq, where L is the length of the lattice. Now, using the relationship between omega and q, we can further simplify the energy relationship, that is E is equal to 2 L by pi A integration 0 to omega max h cross omega by exponential h cross omega q by k t minus 1 root over of omega max square minus omega square d omega. Now, since we got the energy for this particular lattice structure, we can easily find out the specific heat for the one dimensional silicon lattice, and that we can get by integrating the energy with respect to temperature. That will give us the specific heat for silicon lattice. And as you can see in the diagram, the two curves that we get by using Debye relationship and the relationship that we currently discussed, we can see that there is a difference between the two curves, and curve A represents the graph that we got by using the discussed method, and curve B represents the graph that we get by using Debye theory. So, curve A matches with the experimental value much closer than curve B. So far we discussed a monoatomic one dimensional lattice, and the example that we took is silicon. Now, the next example that we will consider is gallium arsenide, which is a diatomic lattice structure. Here there are two types of atom having different mass. One can be denoted by capital M and the other one can be denoted by small m. This is also a one dimensional infinite lattice structure, but here in this figure, in this particular slide, you can see we have taken a small section of this one dimensional infinite lattice. So, these atoms in the lattice, they are arranged regularly with a equal spacing between two adjacent atoms. Now, because we have two different types of atoms, we have to use two different equation of motion, and here also we are considering only the interaction with the neighboring atoms. So, if we use the equations of motion, then we will have two different equation of motions for two different masses. So, for capital M, the equation of motion is m x 2n double dot is equal to f x 2n minus 1 plus x 2n plus 1 minus 2 x 2n, and for small m, the equation of motion is m x 2n plus 1 double dot is equal to f x 2n plus x 2n plus 2 minus 2 x 2n plus 1. The equation can be solved by considering the following two solutions, that is x 2n is equal to a exponential minus I omega t minus 2n q a, and x 2n plus 1 is equal to b exponential minus I omega t minus 2n plus 1 q a, where a and b are the amplitude of the waves. Now, using these two solutions in the equation of motion and simplifying the solution, we can get the following equation, that is omega square is equal to f 1 by small m plus 1 by capital M plus minus f 1 by small m plus 1 by capital M whole square minus 4 sin q a square by capital M into small m and square root of the whole. So, now there are two angular frequency we can get from this particular equation, and we can denote one as omega plus and the other one as omega minus. So, for this omega plus and omega minus, they represent two different branches in the dispersion curve, and the branch that is represented by omega minus is called acoustical branch, and the branch represented by omega plus is called optical branch. Why the names are so, we will discuss a little bit later. For capital M greater than small m, we will have omega plus is equal to square root of 2 f into 1 by small m plus 1 by capital M, and omega minus is equal to 0 at q is equal to 0. Whereas, for a periodic function of omega within the region of minus pi by 2 a to plus pi by 2 a, we can find out all the vibrational modes for this particular example. Now, if we want to find out what is the value of omega at the boundary, that is at q is equal to plus minus pi by 2 a, we will find that omega plus is equal to root over of 2 f by m and omega minus is equal to root over of 2 f by capital M. As the capital M by small m ratio increases, the branch gap also increases. This is clearly shown in the following diagram in this particular slide. So, from A by B ratio, we can find out the physical difference between the branches. As you can see, at q is equal to 0, we find that A is equal to B for acoustical branch and minus M A is equal to small m B for optical branch. So, for acoustic branch all the particles move in the same direction, and for optical branch all the particles move in the opposite direction. That is what the physical meaning that we get from the following curve. Now, at q is equal to plus minus pi by 2a, for acoustical branch all the lighter particles are at rest, and for optical branch all the heavier particles are at rest. Now, if we calculate the energy that is absorbed in this crystal, then we find that the energy that is associated with the frequency in the electromagnetic spectrum is the energy corresponding to the IR region. So, this particular crystal absorbs energy from the IR region. Now, after getting all these information, we can find out the specific heat for this particular crystal by using the method that we used for silicon crystal. Now, we want to understand the concept of thermal conductivity. Now, heat flow from hot to cold part of a substance is thermal conduction. Now, the ability of flow of heat is characterized by thermal conductivity, and mathematically we can represent the thermal conductivity by the following equation, that is q is equal to minus k dt by dx, where q is the heat flux, that is the amount of heat that is emitted from a particular area, and k is the thermal conductivity, and dt by dx is temperature gradient. Now, the negative sign represents heat flow from hot to cold. Now, the total thermal conductivity for a solid can be represented by the thermal conductivity due to lattice plus thermal conductivity due to electron. So, K is equal to KL plus KE. Now, the next thing that we want to discuss is thermoelectricity. Now, heat difference at 2 points in a given metal gives rise to a potential difference, or it is vice versa. If there is a potential difference, we can expect a generation of heat difference. Now, this particular phenomenon can be explained by using 3 coefficients, that is thermoelectric power, Peltier coefficient and Thomson coefficient. The 3 coefficients are connected by Thomson. So, if we know a particular coefficient and if we want to find out the other coefficient, then we can easily use the Thomson relationship to get the other coefficients. Now, what is thermopower then? It is the efficiency of a material to generate voltage for a given temperature gradient. So, when heated at one end, what happens is that the free charge in the metal, which are in general free to move in the metal surface, they start getting higher energy and will start moving to the colder end. So, there would be a surplus amount of positive charge in the hot end and surplus amount of negative charge in the cold end, and because of the concentration of positive charge in one end and negative charge in the other end, there would be a potential difference between the two ends, and this is represented by the value S, that is equal to delta V by delta T, and the unit for this is volt per Kelvin. But this voltage that we obtain is so small, the unit usually used is microvolt per Kelvin. Now, it can be a positive value or it can be a negative value depending on the charge carrier. Now, what is Thomson effect then? So, for a given metal, if we maintain two different temperature at the two ends of the metal, let us say for this particular diagram, let us say T2 is greater than T1, then we will find that there is a current that is flowing from T2 end to T1 end, and because of this current flow there would be a transverse heat flow. That means, the heat flow will be perpendicular to the direction of the current flow, and this heat flow can be evolved or it can be absorbed. Now, in some materials it is evolved and in some materials it is absorbed. Now, the materials where it evolves is copper, silver, zinc, cadmium and so on, but the material where it is absorbed is iron, cobalt, nickel, bismuth and so on. But there are some materials in which neither it evolves nor it absorbs. For example, lead is the best example where there is no absorbance or evolve of heat when we are maintaining lead at two different temperature and we are allowing a current to flow through it. So, this particular phenomenon can be understood by the band structure of the solid, which we will discuss in the subsequent sections. So, in Thomson effect, the total heat flow in the solid can be represented mathematically by the following equation, that is Q is equal to rho j square plus mu j dt by dx, where the first term is due to Joule heating and the second term is due to Thomson heating, where Q is the heat produced per unit volume, J is the current density, mu is Thomson coefficient, rho is the resistivity and dt by dx is the temperature gradient. Now, the next effect that we want to understand is Seebeck effect. So, this is a phenomenon where we have two different materials forming junctions, two different junctions, and if these two junctions are kept at two different temperatures, then at the other end there would be a development of potential difference. It can also be possible to have this kind of effect in a single junction. That means, if we have two materials which are connected to each other and at the junction if we keep these two materials at a particular temperature, then at the cold end we will find there is a potential difference which is generated, and this can be represented by the following equation, that is V is equal to integration T1 to T2 SB minus SA, and if the temperature is constant then V is equal to T2 minus T1 into SB minus SA. Next effect is Peltier effect. So, in a bimetallic circuit, when a current flows, there exists a temperature difference between the junction. So, in the given diagram, T2 is greater than T1. So, the Peltier heat absorbed by the lower junction per unit time is Q prime is equal to NAB I, that is equal to Na minus Nb into I, where Na and Nb are the Peltier coefficient and I is the current in the circuit. So, the Peltier coefficient tells the amount of heat carried per unit charge through a given material. Now, we know all the three different types of thermoelectric power generation. These three can be interrelated by using Thomson relationship. So, Seebeck effect is a combination of Thomson and Peltier effect. So, Thomson gave the relationship between mu S and N by using the classical thermodynamics, which is N is equal to S into T and mu T is equal to T into ds by dt. So, if we know one coefficient, we can easily calculate the other one. So, the laws of thermodynamics usually do not apply to thermoelectric, but Thomson relationship is an exception for that matter. So, in today's talk we discussed very important features of solid, such as we found out the specific heat for monoatomic and diatomic lattice structure, and we found that Devi's law cannot to finding out the specific heat for these solids. We also understood the concepts of thermal conductivity, and we discussed in nutshell what is thermoelectricity and how it can be generated, what are the different methods. And finally, we came up with a relationship which correlate all the three different types of thermoelectric power generation, and it was given by Thomson. Hope you would have liked today's lectures, and thank you for your attention.